Good afternoon, dear students. Today we'll be talking about order of a group, because previous classes was on group, different types of group, lot of examples we have done on groups. So let us discuss on order of the small descriptions of the order of groups. After that, some assignments of groups order, and after that we'll go to the move to the subgroups. So let us first define group, order of a group. Let G star be a group and A belongs to Z. If there exists a positive integer n such that a to the power n is equal to e, where e is the identity element in the group, then the smallest such positive integer is called the order of a. Emphasize on order of a. If no such positive integer exists, then we say that a is of infinite order. So I'm highlighting this line that order of a and infinite order. So order of a is generally denoted by order of a. This is the symbol of writing order of a of an element. So this symbolically defines order of a. Now suppose, for example, you know the group of 1 omega omega square. It's a with respect to multiplication. So what is the, if I with respect to multiplication, so what is the order of omega? Omega will be 3. Order of omega will be 3 because omega cube is 1 and 1 is the identity element in the group, so on. And if we talk about a modulo group Z6 with respect to plus, then what is the order of 1? It will be 6 because 1 bar is the identity element, like this. Now another thing is that what is the order of the Klein's 4 group? We know that except the identity, all the elements have order 2. So order of A is 2, order of B is 2, order of C is 2. So in that way, Klein's 4 group, we can say that except the identity element, all the elements A, B, C are of order 2. This is easily verified because Klein groups have 4 elements. So after that, we'll discuss about a very important theorem. This is a very important theorem. Let A be an element of a group G star, then order of A is exactly equal to the order of A inverse. So order of A is equal to the order of A inverse. If order of A is n and a to the power m is e, then n is a divisor. This is a very important property. If order of A is n and a to the power m is e, then n is a divisor of m. Next, number 3, if order of A in A is n, then a square and dot a n are distinct elements of G. So you have a distinct set of elements a square continuing a n. Number 4, if order of A is n, then for a positive integer m, we can write this relation. This relation is very helpful to find out the order of an element. Suppose order of a to the power m. How will you find out the order of a to the power m? Just simply divide n by GCD of m n. Greatest common divisor of m and n. We'll apply so many problems are there in your textbook. You can find out, and proof of this theory, parts of these theorems you can find out easily. You can prove it, you can try it for those problems. If order of last property, if order of A is n, then order of A to the power p is equal to n if and only if p is prime to n. Let's come to the next. So this is the important theorem we are talking on. Next let's come to the few questions on that using order. Order. So you have a following assignments for the order. Let's try it. You try it better. After that we'll discuss. So if suppose in the first question you have a square is e, a star b, a star b, a star a is equal to b to the power 7. Prove that b to the power 48. It should be, there is a writing mistake. Its power will be 48 equal to e. So a lot of problems on the order, and also you have some matrix multiplication. Fifth one is very important questions. Students should try this. 6 7 abelian group. If each element except the identity of a group B of order 2, prove that the group is abelian. So in a group G star, if this is holds, prove that the group is abelian. So you have 10 questions for your assignment. Next we'll move to our subgroup. So let's subgroups. Then we discuss about the subgroups. Now before we define a subgroup of a group, so let us give some information. Let G star be a group and H be a non-empty subset of G. H be a non-empty subset of G, and H is said to be closed under the binary operation star. Look at that, it's a very important line, that H is said to be closed under the binary operation star if A star B belongs to H for all A B. That is a closure property, you know that. Then the restriction of star, this is the new thing we are going to learn. Restriction of star to H cross H is a mapping. What is that? Is a mapping from H cross H to into H. So restriction of star is nothing but a mapping from H cross H into H. Thus the binary operation star defined on G induces a binary operation on H. Thus H star is a groupoid. If H star is a group, then we call H is a subgroup of G. So let us now define in a proper way. So what is the definition of subgroup? Let G star be a group and H be a non-empty subset of G, then H is called a subgroup of G star if H is closed under the binary operation star and H star is a group. So this is the definition. Examples. So every group G has at least 2 subgroups, that is the group itself, and if you take only the identity element, these are called trivial subgroups. So next you can put an example of Q comma plus, that is set of rational numbers with respect to addition is a group, you know that, and Z is a non-empty subset of Q. Set of integers is a non-empty subset of Q. So we can say that Z comma plus is a subgroup of Q comma plus. So set of integers with respect to addition is a subgroup of set of rational numbers with respect to addition. This is an example. You can take a note of that this is an example of an infinite group having an infinite subgroup. Next we'll have example of a if students will ask a question, can you give me an example of a finite group having commutative subgroup? Yes, this is very, very important. Finite group, non-commutative, finite non-commutative group. Example of a finite non-commutative group having a commutative subgroup is a very, very important example. Yes, there is an example. A3 is the commutative subgroup of the non-commutative. A3 is the alternative group, you know that, and S3 is the symmetric group S3. So A3 is a commutative subgroup of the non-commutative group S3. More examples will look forward. So there is a theorem, H star be a subgroup of G star, then the identity element of H star is the identity element of G star. Exactly, the identity element of H star is the identity element of G star. And number 2, if A belongs to H, then the inverse of A in H star is same as the inverse of A in G star. Now the important thing is that what is the necessary and sufficient condition that H is a subgroup of G? There are several 2 theorems. So I will talk about the first theorem. Let G star be a group, a non-empty subset H of G forms a subgroup of G star if and only if, look at the condition, it's a closure property. A belongs to H, B belongs to H implies A star B belongs to H. Number 2, A belongs to H implies A inverse belongs to H. So these are the necessary and sufficient conditions for H to be a subgroup of G. That means if these conditions follows, H is a subgroup of G, H is a subgroup of G, means these two conditions follows. Another conditions, if you clubbed these two, if you don't have to prove these two things, just you need to prove only one property, that is the next theorem. That is the next theorem. This is also a necessary and sufficient condition. That is, if you can prove A belongs to H, B belongs to H, implies A star B inverse belongs to H, then this is also the necessary and sufficient condition. So we'll talk about a necessary and sufficient condition of a subgroup of H to be a subgroup of G. Now there will be several questions will be asked. If H and K are two subgroups, can we say H intersection and H intersection K is a subgroup of G star? Yes, H intersection K is always a subgroup of G star. That is already proved in the following very short proof we have, because H intersection K is non-empty. Why? Because E belongs to both H and K, so E being the identity element. Now A, B belongs to H intersection K, then A belongs to B, AB belongs to H, as well as AB belongs to K. Now H is a subgroup. We can easily say from the necessary and sufficient condition that A composition B inverse belongs to H and A composition B inverse belongs to K. So naturally A composition B inverse belongs to H and composition B inverse belongs to K implies A composition B inverse belongs to H intersection K. So implies H intersection K is a subgroup. But union, it's not necessarily a subgroup of G. Not always. Not always. So there is a contradiction. There is an example, counter example for that. Suppose you take set of integers with respect to plus and two subgroups 2z comma plus 3z comma plus, then you can show 2 belongs to H intersection K, 3 belongs to H intersection K, but 2 plus 3 does not belongs to H intersection K. So union is not necessarily a subgroup of G. Union will be a subgroup of G if and only if either H is contained in K or K is contained in H. So this is very important theorem. Students should try to prove this theorem. So union will be a subgroup of G if and only if H is contained in K or K is contained in H. So today I finish my lecture up to this. Thank you all.